Haas recently took to track with their brand new VF23. And in this video, we're going to go from front to the back of the car, looking at all the new little aero details on the car, what they are, what they do, and why Haas might have fitted them to this car. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19, and 20 Formula 1 seasons, and I now work as an aerodynamics consultant, designing aero kits for race cars in all different classes all around the world. As per usual, this video comes with a disclaimer that no one can truly predict accurately all the aerodynamic flows around something as complex as a Formula 1 car by eye, so this is at very best a very educated guess. But still, I'm going to try my best to break down the car and analyze what might be happening and what the compromises in designing each part might be. Okay, so starting off with the front wing, what I've done is I've collected a picture of the new car over here, and then we've got some shots of the older car here. And what I wanted to emphasize is that the front wing philosophy is quite similar. You can see that we still have that sort of cranked centerline section through the middle portion along there, and then we back off at the edge along there into a progressive drop down to a very backed off section by the time you reach the outboard portion. What has changed though is that the peak of the wing, or the most cranked part of the wing, is now much further inboard. You can see that out here we have it cranked much further outboard and then we drop down, whereas on the new version we actually start dropping down from much further inboard. Now there's a few things that this could mean. One is that they found a lot of performance from increasing the downwash down towards the tire. So obviously all these wings are making a bit of upwash, but the more we back this off, the more downwash we get into the tire. It can be a little bit better for the squirt management and some other features around there. The other thing is this could be more indicative of the fact that maybe they found more load in the forward floor along here. So maybe they need less balance from the front wing. So they're able to back off more of the front wing to achieve that balance, because it's hard to tell from the images, but the centerline does look pretty similar in its level of crank compared to last year. And that could be due to them either finding more performance on the forwards floor, or it could be because the rules changes have lifted up the rearwards corners a little bit. Maybe they've got a little bit less balance on the rearwards portion of the floor, so maybe there's naturally more balance on the forwards floor. So maybe they just don't need as much balance from the front wing. So they have the liberty to back it off in a section, and maybe it's not too profitable to back it off in the center. It's much more profitable to back it off at the outboard portion. And of course, there's always the discussion of outwash distribution and vorticity casting, where obviously where we have the transition point is going to change how we're casting our shear layer off the front wing. Obviously, this is quite a soft wing in terms of its transitions. It doesn't have many harsh transitions apart from this little bit out here. So it would be very hard for me to predict exactly how that vorticity is going to be shed, but they might be playing around with where their overall vorticity ends up downstream. And then also the amount that they're cranking outboard is going to change how the outwash profile goes on the wing, as well as the downwash profile. Some other notes on the front wing, just around the end plate. You'll see that we've ditched the old style tubicles off the front. It used to have these little wavy tubicles, which tubicles, there's a fair amount of research on them because they're on the front of whale fins and stuff like that. They're a bit of a way of improving separation further downstream. They can help a bit with boundary layer mixing. They're not the best vortex generator out there, but they are an option where you're quite rules limited in this area. But they've obviously ditched those. They've gone for a more conventional smooth edged end plate there and there. And of course, they've also ditched their canard that they were fielding last season, which sort of turned into more of an outwashing gurney at the back of the end plate. Instead, they've gone for this more conventional canard or dive plane approach along the side here. So those are notable changes, and that makes the whole setup a little bit more conventional on the front wing end plate. Moving a little further rearwards, I'd like to direct your attention towards the front Caketin, because this is something that there's actually been a fair amount of change that I'm not sure that most people would have noticed, because it's fairly hard to spot. On the old front Caketin, they had a scoop that very much caves in here, and then it comes out along here, and their track rod comes in about here on the scoop. It's slightly lower, but it's in that ballpark, is about where the track rod comes in. And this year, they've actually removed the track rod from there. The track rod is no longer on the scoop, and you can see this in a few different shots, but the track rod basically doesn't come in on the scoop anymore. And so they've gone for a much wider scoop here. You can see that their brake scoop comes the whole way out like that. And my suspicion is, based on the images, it's quite hard to see, but I think that the track rod has migrated to down here, I think is where the track rod is, just in front and slightly above of the lower control arm. Looking at this shot here, you can just see the little dividing line along there and there too, which is what I think is the split line of the track rod to the control arm. And you'll also see in this shot here too what looks like member 1, member 2, and then track rod just in front of it there. So why would they do a change like this? Well, there's a few potential reasons. One is if you have a look at what I think is the track rod along here, you'll see that the nose is quite sort of wobbly on it. There's a lot of alignment things going on there. So they're probably aligning that to whatever the upwash profile is from the front wing. And so chances are what they're doing is that they're using this to form a bit of a cascade with the lower control arm. So if you imagine if we're looking in side view, what we'll have is that we'll have the first element of the track rod. Then we'll have the second element, that's the first bit of the front control arm, and then we'll have the third element over here, which is the rear bit of the front control arm. Those aren't great airfoil profiles, but you get the intent. And so we'll have some upwash coming off the front wing, and these will try and turn that back into downwash. They'll generate some pressurization underneath under here, and a little bit of downwash underneath them. And the reason why I can see you might want to move your track rod down here, discussed this a little bit last year, but with the track rod you can help support the first element of the control arm, so you can help to suppress some of the separations on the top back half of that there. And by that you can reduce the losses, you can crank that whole system a little bit more. There's legality limits on how far you can crank it, but you can still improve the performance of this system by essentially slatting the control arm with the track rod. And by doing that, we can clean up the flows further downstream. We can increase the downwash and increase the pressurization underneath. And those features of increasing the downwash and the pressurization down here towards the tire squirt is that the tire squirt can get suppressed by having additional downwash and additional pressure alongside the tire. You'll also improve the downwash that goes down towards the floor leading edge at the back, which can improve the suction on the floor leading edge and the general performance of the floor leading edge. The other thing that the relocation of this track rod gives you is it gives you a little bit more design freedom on the scoop. You don't need to worry so much about the track rod junction with the scoop, although obviously these guys still have to worry about the push rod junction with the scoop. But you don't have to worry about that additional junction being on the scoop. So you have a little bit more design freedom on the scoop, where currently Haas goes and has their scoop pass through the shield like most teams, and they've gone and fattened this scoop up a lot, and maybe they've got a slightly cleaner flow downstream, or maybe they're doing something else with the management from the scoop, but it's allowed them to change their scoop direction a little bit. Looking a teeny bit further rearwards, what you'll see is that the top of their bargeboard region has a really aggressive outwashing section towards the back of it that's quite obvious in other shots as well. This is most likely to try and enhance the outwash of that mid-wake around there, get a little bit of pressurization increase on this particular side of it, and enhance that outwash there. And of course there's going to be a trade between that outwash there and also generating a strong and lossy vortex on the top edge, which will run down the floor and generate some local lift on the top edge of the floor by vortex-induced suction. And also it could be quite a bit of loss that gets ingested by the floor further downstream. But that's the trade for having that high level of outwash in that particular region. Going back towards the side pods, I don't want to talk too much about the side pods because they are very, very similar in design to the Ferrari ones that I analyzed last year. And if you want to get some more information on how they work, you can go and watch my Ferrari analysis video from last year. But they do have a little design tweak that I want to go through, which is this particular front lip portion here. So I'm just going to talk briefly about that particular bit there. Look at this comparison shot to the Ferrari. What you'll see is that on the Ferrari, both lips go the full length forward, presumably pretty much all the way to legality, whereas on the Haas, only the lower lip goes the full length forward, while the upper lip is paired further rearwards. This really brings it more into the style of the Red Bull side pod inlet, which can have a lot of different things happening aerodynamically on the front of it, depending on the specifics of the onset flow, whether it's upwashing, downwashing, how much that's occurring, and also the specifics of the ducting behind it, whether the inlet pressure is higher or lower than the stagnation pressure below the side pod. So anyway, I go into this a little bit more in detail in my Red Bull video. I suggest you have a look there if you want to see an analysis on how this side pod inlet style works. Now moving up a little bit more, let's chat about the mirror. Now last year Haas ran this particular style of mirror with an enclosure around it, a sort of annulus. This year they have taken that annulus approach and then they've cut out the outboard portion and added some little vanes. So there's little drop vanes down there, and then the end bit of the annulus turns into a third outwashing vane there. In previous years, quite a few cars have run this annulus style mirror housing, and a lot of what they're doing is making use of the fact that the housing rules are pretty loose. As long as you're within the volume, you can do pretty much anything you want. And the main advantage of this particular style of mirror is that if we look in side view, if you imagine your reflective surfaces here, and you go and have your mirror like that, and then you go and have a housing that is essentially an airfoil like that, what happens is you have your air that goes around here and it blows in, and these can actually produce a lot of inwash there. So the air will go around there, and it can help shrink and control and stabilize the wake behind the mirror. And if you can shrink and control and stabilize that wake, what you'll do is you'll locally decrease drag on the mirror, which is obviously a plus, and you will also decrease the size of the wake. You'll reduce the losses of the wake further downstream, which means that your devices downstream that would be hit by this wake will perform a bit better. So why has Haas transitioned into this 3-vane outwashing setup? Well, this setup is actually quite similar to what Ferrari was using last year in this particular portion of the mirror. And it's in a way not similar to how the outer portion of the mirror for the Red Bull and the Aston Martin both worked. Basically, we've more or less established at this point that all the teams seem to be trying to do the same thing here, generate a good chunk of outwash, presumably to outwash some of the tire wake. But by having the drop vanes on the mirror instead of vanes that are coming up from the stay on the side pod there, you actually end up with a different direction of vortex rotation. So if you have the stay on the side pod, the vortex will rotate that away. So basically what will happen is that you'll end up with upwash out here and downwash down here. With this mirror style setup, what will happen is the vortex will rotate the other way. So you'll have relative upwash on the inboard portion and relative downwash on the outboard portion, and inwash further rearwards around this back portion here if your structures managed to persist that long. So you can see that it's an opposite direction of rotation because they're both outwashing, but one comes down from the top with a free edge at the bottom and the other one comes from the bottom with a free edge at the top. Now, in terms of the ramifications of that, I think that it's mainly going to play into the specifics of the side pod, and perhaps it's telling that this setup is very similar to what Ferrari ran last year, and this is a very similar side pod setup to what Ferrari ran last year. So there's probably a linking between those two features where those two features combined together must work fairly well. Looking further down at the floor edge, there's nothing too new going on here. We've got a curl here that drops down, then goes into another curl that then goes along here. You can see that we've got just the protrusions of the turning vanes coming through there. We've got 2 turning vanes protruding there. As to why you would want a discrete curl, there's a multitude of reasons. You could end up trying to discretize the vortices off the side, so maybe you're generating a small vortex off here and another vortex off here. There is outwash in this region, but you can end up with a bit of vorticity being cast off these edges. So ramping down and up could split this into 2 separate vortices instead of 1, which maybe is a bit cleaner or better downstream. The other option that's also available is that if you do have an upstream thing like a turning vane underneath the floor and it's generating some losses off it, if you have a continuous ramp through here and the losses come in onto that ramp and then you try to kick them up and expand them, you could overexpand them, which could cause a big old blow up here. So you may choose to dip down the ramp to reduce the overexpansion of those losses. So that's another potential option. So those are 2 ways that they could be handling the flows there. Looking a bit further rearwards, you'll see a design that, again, nothing new for this year. This is something that we saw on Ferrari last year, and I think a few other teams might have run this as well. Basically, you've got a split in the floor here with the floor edge wing, just highlighted in orange there. That's what they're running for their floor edge wing, and basically that produces a slot in the floor. Again, what you'll have when you split the edge up like this is you'll have a discretization of the forward vortex from this region will be split. You'll end up with another small vortex off here and then another one further rearwards. You'll notice that all of this section here is raised up quite high, so there's probably a fair chunk of suction in here that's going to drive a pretty decent vortex there. And obviously being slotted and with this particular bit of the mouth being raised, what we'll end up with is a reasonable chunk of mass flow coming in, and that should end up going into the floor. It should be fairly clean mass flow, and that should hopefully clean up the diffuser depending on how they use it once it gets inside. Looking up at the central bodywork, you'll see that the roll hoop is a little bit different. You can see on the old car it was a little bit fatter, and you could see there's a fair chunk of air going in the top inlet as well as the bottom inlet. In this one, the top inlet is a lot smaller. The whole thing is quite a bit tighter, again looking a little bit more like last year's Ferrari again. And that's a bit of an indication they could have reduced their centerline cooling a bit. But the main thing that interests me about the central engine cover is more around the shark fin region, because that's quite an interesting shark fin compared to the rest of the grid. The Haas shark fin is pretty cut out. You can see that we've got basically to the top of the legality box here, we've got a little notch in there, and then we go down, we've got a trailing edge notch there, and then we go along, cut down, and straighten up here. Then at the bottom, we actually separate off the engine cover here. You'll see the engine cover is actually really tight. It dives down quite hard through there. It's a very tight engine cover. And then in this case, the engine cover bulges back up, presumably to cover some internal components. There must be a few things that are forcing that bulge up there. And what you'll see is that Haas runs a louvered setup. You can just see the tiny serrations along the center line there. This is not dissimilar to what they ran last year, but you can see that they've got these little serrations there. Now, some of that cooling louver setup is presumably going to be to vent some of that centerline cooling. Maybe there's a little bit of additional cooling air that doesn't make it out these side louvers that then ends up going through the bodywork and gets vented through there. But let's talk a little bit about how that shark fin works and why they'd be notching it so hard. Now, this seems like as good an opportunity as ever to talk a little bit about discretization, because I often get asked a little bit about what the vortex discretization is and what that kind of means for the aerodynamics. And what I want to do is just show you a little bit of an example. Imagine that I had a shark fin that was shaped pretty much like that. And then in a corner, I'd end up with a vortex rolling off it. I've got some degree of side wind on it. There's a pressure differential across it. It's going to create a vortex. So I've got one big old vortex coming along here. Now, that vortex may, if it's overpowered, choose to detach a little bit early. So it could detach up here and go over here. Or depending on the shapes and the specifics of the flows around it, it may continue attached and roll down the surface like that. Now, when we have one big vortex structure, generally speaking, what ends up happening is that we end up with quite a large, powerful, and lossy vortex structure. Now, an alternative shark fin geometry that I can show you is that if we go and we notch there, and we have a separate shark fin there, it goes back, and then we continue like that, what will happen is we'll end up with two vortex structures generated. We'll generate one here, and that will cast off, and then we'll generate another along here, and that will cast off. Now, generally speaking, because each of these two vortices are smaller in initial size and magnitude, generally speaking, not always true, but most of the time, each vortex will be a little bit cleaner. So you'll have two smaller vortices, but each vortex will be cleaner and have a greater total pressure in it than this one big structure. What happens with vortices that rotate in the same direction is that as they go further downstream, they'll eventually merge into a big structure. And if we were in a perfect world where we had no viscosity, the energy of these two vortices merging would end up being pretty much exactly the same as this big structure here. Now, in the real world, there's a little bit of energy loss when they have that merging process, but more or less, the sum of the vorticity of these two vortices should be about the same as this, and as we go downstream, say over to here, they will have merged into just one vortex structure. So it's kind of equivalent downstream to just having one vortex structure. The two trades you have to balance with this is that merging the two vortices together in the real world with viscosity means that you lose a tiny bit of energy when these vortices merge, but because you have more energy at the start, even by taking a hit when they merge, you can end up with potentially a better, healthier, and stronger structure than one large single vortex. The takeaway from that is that two vortices rotating in the same direction downstream will merge into one vortex that is roughly the same power as the two combined. Now, the reason I say it's a balancing act is because obviously there's a few more factors at play here. One is that this particular angle along here, how we've swept this particular angle in, often when you angle out planform more, it forms a more aggressive roll-up of a vortex, which is usually a little bit more lossy. By the same token though, we've also cut away planform here. So we've reduced the overall power of the fin and presumably the overall pressure differential as it is a finite element. So there's a lot of factors going on here. The other one is that splitting this up in this way allows you to manipulate the vortex positioning differently to having one large singular one. So in this case, potentially having this split on the lower thing means that we drag the bulk of the vorticity downwards. And by doing that, that means that maybe where a single fin may have crashed the vortex into the rear wing. Maybe by splitting this down, maybe we've just been able to sit it below the rear wing. That could be a potential option. There's just a lot of factors at play here, and you can see why you need CFD or wind tunnel to work out exactly what's going on and what the trade-offs are. The other feature that we have going on this particular setup is that because we've got the cutout on the bottom where the cooling louvers are, we'll end up with a counter-rotating vortex. We'll have a vortex rotating off the bottom in one direction, and we'll have a vortex rotating off the top in the other direction. Now, what this vortex pair could do is that they're going to essentially result in a wash towards the shark fin, and that could suppress some of the losses that could potentially be forming on the shark fin's surface here. So you could suppress the losses with this, basically get a vortex-based attachment, in addition to vortex-induced suction from both of these vortices on the surface here. And that maybe results in a better trade in terms of being a more efficient system, in terms of side load and overall health and cleanliness and total flow energy out the back of it. As always, can't give a perfect prediction on it, but these are the trade-offs that would need to be considered here, and I'm sure that Haas would have run through these different thoughts when they were designing this particular component for this car. And that's my analysis for the Haas VF23. Well, that's all for this video. If you liked it, don't forget to hit that like button below and subscribe to my channel for more content like this. Leave a comment below on what videos you'd like to see next, and hopefully, I'll see you next time.